Chale, it's this paper, okay? Can you see the screen now? Can you hear me?
Yes, sir.
Okay, so this is the latest one. This is March 2023. And I said the last question, you want to do the last question first. So just 1 second. As I for this one, not really sure if there is a marking scheme for this. Just a second. Probably not. अच्छा now
सर है लेकिन वो वर्ड पे खुलती है.
अच्छा तो ठीक है, एक सेकंड में देख लेता हूँ. So somebody should open the marking scheme, okay? Because I don't know what I've never actually done this paper. Now a student uses thin layer chromatography, okay? This is it only has 6 questions, by the way. Achha, so a student uses thin layer chromatography to analyze. Thin layer chromatography is the same as paper chromatography. It's the same basic idea that you have RF values. The only difference is that you have a thin layer, a metallic plate, and in that metallic plate there's a gel, and the dyes, they would stick to the gel. If a dye does not stick, it will continue to travel along with the solvent. If it sticks to the gel, it will stop moving. So the mixture is placed over here, and everything, the mixture gets separated into different components. Suggest a compound that could be used as a stationary phase in the experiment. That's the gel, and that's silica or aluminum oxide. That's usually used. And the table shows RF values for different metal cations, which when separated by TLC using water as a solvent. So the RF values are given. The RF value, what's the definition of RF value? That's
the height of the acid over the solvent. The distance.
Dye or component. It's the distance traveled by the dye or component from the baseline over the distance that the solvent travels. So 0.4 means that if the solvent 0.4 means if the solvent travels a distance of 1, it's 0.4 means that which one is 0.4, by the way? So the solvent is traveling a distance of 5. So 0.4 means that the dye distance, the dye that travels divided by the distance that the solvent travels, which is 5, the answer comes out to be 0.4. So it's 5 times 0.4. That is the distance that is traveled by the dye. So what is 5 times 0.4? That's going to be 2. So M is probably having an RF value of 0.4. Okay, so this one is definitely M. So he wanted to, so the first one is M. He wanted to identify the cation that causes spot at M. So that's this one. And you have to explain your answer. So I think you have to just tell them that the RF value is 0.4. So tell them that it is going to be 0.4 if it's 2 over 5. So RF value is basically 2 over 5, which is basically equal to 0.4. So that means the dye travels a distance of 2, whatever this is, 2 centimeters, I think. That's the next one. The student repeats the experiment using butane-1-ol as the solvent. The metals do not travel as far up the TLC plate in this experiment. Suggest why the metal cations do not move as far up the TLC plate when butane-1-ol is the solvent. So we would first have to compare this with what was he using before? What was the solvent? So previously it was, previously the solvent was water. And now he's saying that the solvent is butane-1-ol. So previously the solvent that was moving upwards, that was water. But when he changes to butane-1-ol, the question states that the dye does not travel a very large distance. That means The ions are not very soluble in butanol. That's probably going to be the only explanation, that the ions are not going to be very soluble in butanol. 1 mark, probably that's it. TK. Let me open the marking scheme as well, like what words he's using. Okay, so this is the question number, that's question number 1. Just a second. Okay, uska with her, they just had to tell you it's 205.4, so that's the answer for this. And that's it. That's soluble in butanol. That's it. I said next one. Next one is students space the TLC plate with KSCN. The color of some of the spot changes as some of the metal ions undergo a ligand exchange reaction. So what is the ligand in this case? Now previously they were all aqueous, so that means all these metal ions which were aqueous, like copper 2 plus. Copper 2 plus aqueous is a blue colored solution. So previously what happened was that you had copper and it was surrounded by water molecules. So that was the complex that was formed when copper 2 plus was aqueous. But now you've got what kind of ligand does KSCN have? It's got CN minus 1. That's what the ligand is. So the water molecules are going to be replaced by CN minus 1. So the color of some of the spots changes as some of the metal ions, cations, undergo a ligand exchange reaction. Identify the ligands involved in the ligand exchange reaction. So the water ligand is replaced by, put the lone pairs, by the CN minus 1. Okay, so KSCN will have that ligand. Then he says in the third experiment, the pH of the mixture of the metal ions is kept constant using a buffer solution. So I guess that's a buffer solution. The student prepares the buffer solution by mixing an alkali with 50 cm cube or 0.1 mole per dm cube of this thing. And what, by the way, is this thing? This thing is drawn over here. So it's a carboxylic acid. So it's got a carboxylic acid group that's attached to it. So this thing over here, this one is your carboxylic acid. And it's got a pK value of 5.4. So you first have to figure out what is the reaction that's going to happen. The reaction that's going to happen is that, this carboxylic acid is going to react with exactly 1 KOH. So it's going to react with KOH because there's only 1 carboxylic acid group. And its H is going to be replaced by K plus 1. So what's going to happen is that this molecule over here, C8H5O4, will now be H4. There's going to be 1 H replaced. O4, and now you're going to have 2 Ks. So the carboxylic acid is going to get neutralized by KOH. And one thing that's going to be produced is going to be water. Okay, so remember, KOH is going to come in and it's going to neutralize this carboxylic acid. Okay, so that's going to get neutralized. Is this part clear? अच्छा, अब उसके बाद ये कि calculate the pH of the buffer solution. So the first thing is you have to figure out what is the buffer solution that's being formed. Can anyone calculate the moles of KOH that are being added? How many moles of KOH are being added? 20 times 0.15 concentration times volume divided by 1000.
3 into 10 raised to power minus 3.
So you're adding 3 into 10 to the power minus 3 moles of KOH. And how many moles of this molecule did you have? 50 into 0.1, that's that's 5 times 10 to the power minus 3, right?
Yes.
So that's 5 times 10 to the power minus 3. Now, clearly the KOH is not in excess. It's not going to completely react. So there's going to be some of the acid that's going to be left at the end. So what will happen is that just to write a more simplified equation, this is what's going to happen. This is your carboxylic acid. Initially, I mean, this equation over here is kind of like, looks more complicated. So I'm just simplifying it. You have your KOH, they're going to react together. It's going to form the carboxylic acid part will neutralize and it will form water. Now this is 3 times 10 to the power minus 3 moles and this is 5 times 10 to the power minus 3 moles. So at the end of the day, 3 times 10 to the power minus 3 is going to completely react. All of it is going to react. And so how much of the carboxylic acid is going to be left? 3 will react with 3. So there's going to be 2 times 10 to the power minus 3 moles of the carboxylic acid that's going to be still left. And 3 will react with 3 to produce 3 times 10 to the power minus 3 moles of this. So at the end of the day, what you have is you have a weak acid, which is your unreacted carboxylic acid, which is 2 times 10 to the power minus 3 moles. And you also simultaneously have the conjugate base, which is the salt, which is 3 times 10 to the power minus 3 moles. Your K expression is this, that it's the I mean, your equilibrium is the same. It's basically the K plus 1 is a spectator, so we can like ignore that. So the equilibrium between the salt and the carboxylic acid is the same equation. It's the same acid dissociation equation. So it's going to be product concentration, which is 3 times 10 to the power minus 3, multiplied by H plus 1 concentration, and divided by 2 times 10 to the power minus 3. And we also have the value of K. They gave us the value of pK, which is 5.4. So K will be 10 to the power minus 5.4. pK is the log expression. So if you take the anti-log, it's going to come out to be 10 to the power minus 5.4. To find the concentration of H plus 1. And then find the pH.
(2.65 into 10 raised to the power minus 6).
pH 2.65. That's take the negative.
Concentration.
5.58.
Yes, 5.58.
So it's coming out to be 5.58. I mean, the equation made it look slightly complicated, but this was just the carboxylic acid getting neutralized by KOH. The buffer was formed after the neutralization had happened. That some of the carboxylic acid was left because it was in excess. The KOH had all reacted, and some of the salt was produced. So you had the conjugate base, you had the carboxylic acid. So you had the salt and you also had the carboxylic acid. So the equilibrium was the same, and you use the K expression to figure out the pH. So that's about it. That's the question. So that was the last question of this paper. So we're now going to do question number 5. This is a question number 5. First thing, it's an alcohol, a secondary alcohol, it's an amine, it's a chlorobenzene. Okay, so this molecule. Describe and explain the shape of benzene, and your answer include the bond angles between the carbon atoms. So one by one, you have to describe what benzene is. So what is the bond angle in benzene?
120.
120.
Okay, that's 120. What is the hybridization?
sp2.
sp2.
Okay, that's sp2. So how many sigma bonds and how many pi bonds? Okay, so what you could do is you can actually sketch one benzene. So each carbon atom is making sigma bonds, right? There's sigma bonds. All of them are 120 degrees, right? So these are all sigma bonds. Not really sure how many marks is this. This is like just 3 marks. So we don't have to. I mean, sometimes you get a 6-mark question on this. So starting with so your p orbitals are going to overlap so that they're going to form pi bonds. So how orbitals form sigma and pi bonds? So you're going to tell them that pi bonds are formed when you have a p and p overlap. A p orbital of one carbon atom overlaps with a p orbital of another carbon atom. That's how pi bonds are formed. So the next thing is how are sigma bonds formed? So this is an sp2 overlapping with an sp2. Remember, carbon's 3 main bonds are sp2 hybridized orbitals. So these are sp2 overlapping with other sp2. So they form a sigma bond. Okay, that's how sigma bonds are formed between carbon atoms. This bond over here between H, that's an sp2 of a carbon atom overlapping with an S of a hydrogen atom. So that's how all the sigma bonds and pi bonds are formed. There will be 6 sp2 overlaps that are going to happen between the carbon atoms. Then carbon's sp2 orbital will overlap with hydrogen's s orbital, and they would form a sigma bond. And the carbon's p orbitals, they would all overlap and they would form pi bonds. Is that clear?
Yes.
So now next thing is in a synthesis of whatever this is, the first step involves the formation of chlorobenzene. Benzene reacts with Cl2, so you need a catalyst. Write an equation to show how Cl2 reacts with AlCl3 to generate an electrophile. So what happens first is that the Cl2 molecule reacts with AlCl3, and that produces a Cl plus 1 electrophile, and AlCl4 minus 1 gets produced. And then the Cl plus 1 goes and bonds with the benzene. So it goes and so the Cl bonds with the benzene. And in the next step, what happens is that the AlCl4 minus 1.
सर Cl ऊपर नहीं होगा?
Okay, people, it's the same thing.
Mm-hmm.
So next step is that the H gives its electrons back. And the benzene electron cloud becomes complete again. Okay, that's going to be your That's the next thing.
सर ऊपर खाली हाइड्रोजन बनेगा.
Honey, ये वाला partner, this one is not necessary. They just wanted to draw an intermediate. That's it. ठीक है, is this clear?
Yes, sir.
सर
हाँ जी.
सर इसका बाई प्रोडक्ट HCl नहीं बनेगा.
हाँ, यहाँ पे HCl बनेगा. अच्छा, but in this case, they were just looking for the intermediate. That's it. ठीक है, so you don't really have to. I mean, if I show you the mark scheme, it's probably going to be just the intermediate. ठीक है. कहाँ पे की है mark scheme? Just one second. This one. Okay, sure, it's loading up. I said next part is name the mechanism of the reaction, step number 2. So what's happening in step number 2? What is this mechanism called?
Acylation.
It is acylation. Like, what's the mechanism called?
Electrophilic substitution.
It is electrophilic. I mean, you can write both. So it's electrophilic substitution. The carbon is very strongly positive over here, so it's going to be attached. It's going to be attracted to benzene. So you're going to have a similar electrophilic substitution reaction. Draw the structure of an isomer of Q that forms as an organic byproduct of the reaction in step number 2. So what is this? So you'll get two isomers. Isomer of Q. So it's either 2. It's either going to get attached to position number 2, or it's going to get attached to position number 4. So the isomer will be this thing over here. Put it on position number 4. That's going to be your isomer. Is that clear?
Yes, sir.
So reactants used in step 2 contain acyl chloride, alkyl chloride, aryl. So again, this is a question that comes very frequently. This is about hydrolysis. We did a similar question last time as well. State and explain the relative ease of hydrolysis of acyl chlorides, alkyl chlorides, aryl chlorides. Now, aryl chlorides are the ones that have benzene, a Cl attached to benzene. Then you've got alkyl chlorides, halogenoalkanes, a carbon chain with a Cl. एक CH2 ऐड कर देता हूँ. अच्छा, उल्टा मैंने लिख दिया. This one is over here, C6H5. Chlorobenzene will have the hardest to hydrolyze. It won't hydrolyze actually. Halogenoalkane, they will hydrolyze, but you would have to heat it with NaOH aqueous and reflux. This one has no hydrolysis whatsoever. And then you have the last one, which is acyl chloride. Okay, that's going to be the easiest. And you'll be asked to explain this. So the first thing is you'll just explain the ends, which is that you'll explain why this one does not hydrolyze, because when you have a benzene, what happens is that the Cl lone pairs, they overlap with benzene's electron cloud, which kind of increases the charge density on the CCl bond. And the CCl bond becomes kind of strong. So that is what you're going to write. Cl lone pairs, they overlap. With benzene pi electron cloud. And then you're going to talk about the bond strength. The CCl bond becomes strong and it repels any nucleophile. So it repels any nucleophile. Water will not be attracted to it. What happens?
क्लोरोबेंजीन का दूसरा नाम क्या बताया था?
Aryl chloride, na?
Okay.
Aryl is benzene.
Okay, sir.
So the other thing is acyl chloride. Why are they easier to hydrolyze? Because the carbon has a very strong positive charge. So the water molecules are very strongly, so it even hydrolyzes vigorously with cold water. Water molecules are very strongly attracted to this carbon that's positive. So there's a strong attraction. So you've got an acyl chloride, and so you're going to talk about that the carbon has a very strong positive charge, slight positive charge, density. There are two electronegative atoms attached to it, oxygen and Cl, which produce a very strong positive charge. So there's strong attraction between the nucleophile and the positive carbon atom. So that's why you have that's why hydrolysis is easy in this case. Give them marks, there's just 3 marks. One would be for the order, one for you can explain this, you can explain this. Let me just check how the marks are distributed. Console part, I think this one. So, or whether you just add 1 mark for this and any 2 from this one. So you just have to explain the 2 things. That's it. Now, the next thing is, TK were 2 electronegative atoms. That's what we wrote. Now, the next one is, okay, draw the structure of Z in the box. So you've got this thing and you have to make this thing. Now, in between, what you have is, this is a halogenoalkane. Like it's a carbon chain with 2 H's. The carbon chain tends to be positive, so it's a halogenoalkane, right? And what you want is you want the Cl to be replaced by NH. That's what you want over here. So this is nucleophilic substitution. There was a reaction that SN1 and SN2 reactions in AS. Chart khol lete hain. So this is part of AS organic chemistry. So SN1, SN2 reactions, halogenoalkanes, they undergo 3 nucleophilic substitution reactions. Halogens can be substituted by OH, they can be substituted by CN, or they can be substituted by NH3, or it could be any amine as well. So all of them can substitute. In this case, it's going to be an amine. It's going to be NH, which has this carbon chain that's attached to it with 3 CH3 groups. So it's going to be this NH and its lone pairs, and you'll have a nucleophilic substitution reaction. The N lone pair will get attracted to this carbon, and the Cl and the H are going to get knocked out. HCl is going to be formed. So draw the structure of Z in the box. So there's one problem, and that's there's no problem. It's just that you have to reduce the ketone as well at the same time. So what will happen first? Will reduction happen first, or will you form the amine first? It doesn't really matter because amines don't get reduced. So I guess that will have no effect on the reaction. So I guess you're going to first substitute this thing, and then in the next step you can reduce the ketone by adding NaBH4. So the reagents that are going to be used is ethanolic, whatever this thing is, C with 3 CH3s, and with an NH2 at the end to get this thing, and reflux. And then what you can do is you can reduce the ketone at the same time. So that's NaBH4. And the ketone part will turn into an alcohol. Is this clear?
Yes, sir.
But order is important. Like, what do you do? Does it really matter if you reduce the ketone first? And then I don't think that would really matter in this case. So we can have a look over here whether the order was important or not. Either order. Okay, they've written that it could be in any order. As a next part, the synthesis produces two enantiomers of this 2-lobutyrol. Define what an
सर
enantiomer.
Z का स्ट्रक्चर क्या होगा?
Z का वही होगा, Cl की जगह put this thing and attach.
Okay.
I mean, अगले step है ना, you've got a ketone. So in the next step, you can reduce the ketone to an alcohol. Well, two changes करनी है ना. One is that you have to reduce the ketone to an alcohol, right? That is NaBH4. That can be done in the next step. Z के अंदर you just have to attach the Cl will go and the H will go. The N will get attached to the carbon over here. ठीक है, is this clear?
Yes.
अच्छा, फिर next part is कि what's an enantiomer?
Carbon atom which is joined with 4 different groups.
ठीक है, लेकिन ठीक है, वो तो हो गया कायल, ठीक है.
Optical isomer.
I mean, they are optical isomers. The synthesis produces two enantiomers. So you need a chiral carbon atom, and that carbon atom would be joined with 4 different groups. What will that lead to? It will exist as two non-superimposable mirrored versions. How Zoha we wrote down it was kind of they didn't actually, they ignored the order. In the marking scheme. I said now define enantiomers. So this is what an enantiomer is. I just suggest one advantage using two enantiomers in this synthesis. Suggest a method of adapting the synthesis to produce a single enantiomer. Now this one. इसके ऊपर मुझे doubt है कि maybe they're looking for the property that there's a property of enantiomers that they rotate plane polarized monochromatic light in opposite directions. So we can write the whole thing because we're not sure what exactly are they looking for. So the main difference is that they rotate plane polarized monochromatic light.
Sir, ये जो आप आखिरी line बता रहे हैं, what does exactly this mean?
इसकी detail तो important नहीं है. What this just generally means is that the two enantiomers, they reflect or they pass light in a different way. ठीक है, plane of polarization is the plane in which the particles are vibrating. So the vibration of the particle changes. This is a rope, and the particles are moving up and down. So they'll start moving at a 60-degree angle. Okay. Do you get the idea? That rotate plane polarized monochromatic light. What does that mean?
Sir, एक दफा फिर repeat कर दें.
This is physics. You've seen ropes, right? It's always drawn like this, that the particles are moving up and down, right?
Yes, sir.
So that's called a plane of polarization, that the particles are moving up and down. So maybe the particles are moving sideways. So that's a different plane of polarization. Okay? So idea clear? What's a plane of polarization?
Yes, sir.
So the plane of polarization
सर
is
इसकी वीडियो अपलोड है YouTube पे.
नहीं, इसकी वीडियो नहीं, बस इसका कुछ भी नहीं पता करना. मैं भी explain कर देता हूँ. This is plane of polarization. ठीक है? You've got a wave. Light है ना, that's wave. ठीक है? Now you're used to the fact that you're used to two-dimensional waves, that particles are vibrating in one direction. ठीक है? Like imagine a rope that particles are moving up and down. But what happens is that the particles are not always moving up and down. They're also moving sideways. Like they'll be coming out of the page, going into the page. Okay? Or they might be moving at an angle of 20 degrees to the vertical, right? Yeah, कोई भी angle. It's a 360-degree plane of polarization that you have. ठीक है? Okay, rope है ना, you could be like producing waves sideways. It's not always up and down. ठीक है? तो ये idea clear है पहला कि what's a plane of polarization? Is that clear?
Yes, sir.
ठीक है? It's the plane in which the particles are vibrating, and that plane could be any plane. It could be vertical, it could be horizontal, it could be at a 60-degree angle or a 20-degree angle or a 10-degree angle. Now, what enantiomers do is that when light passes through a solution that has enantiomers, so when it passes through it, its plane of polarization slightly changes. Sometimes it gets rotated 20 degrees to the right. Sometimes it's going to get rotated 20 degrees to the left. So both enantiomers, they will rotate the plane of polarization of the light in opposite directions. ठीक है कि एक rope है ना, vertical rope, the wave is coming in, and as soon as it hits and goes through the solution, the rope, instead of moving up and down, it starts moving at an angle of 20 degrees to the right, clockwise. ठीक है, is this clear?
Yes, sir.
बल्कि इसका ना एक image दिखा देता हूँ. होंगे कोई images Google में ना. So this one looks fine. Just 1 second. So you can have a look at this one. Okay. Image एक second निकाल. हाँ ये. So you can have a look. So there's an optically active solution. Particles initially vibrating up and down, and then when they pass through it, they start vibrating in a different direction. Not up and down. They start vibrating at a different angle, sideways, horizontal, vertical.
Sir, image में ये लोग 90 show करे, हमें बस 20 याद रखना है.
नहीं 20 भी कुछ भी याद नहीं रखना. You just have to
Okay.
know कि the two enantiomers, they will rotate the plane of polarization in opposite direction with an equal
Okay.
angle.
Okay.
If one of them rotates at 90 degrees to the right, the other one rotates at 90 degrees to the left. Okay. And plane polarized monochromatic light, like normally light particles can be vibrating in any direction. They could be vibrating up and down, sideways, horizontally, 20-degree angle, 50-degree angle, at any angle, right? Normal light is unpolarized. So we're only dealing with plain polarized monochromatic light. This is what it means, that you have a single polarized glasses bhi hote hain, theek hai? So you've got light that is filtered, and that light is only has one plane of polarization. When it passes through it, it's got a different plane of polarization. Which got rotated. So both enantiomers will rotate it in opposite directions. ठीक है, ये clear है?
Yes, sir.
Achha, so that's it. You don't have to go into details with this. Just remember that I just wanted to figure out what exactly did they mean when they wanted to define enantiomers. So the answer for that was, so they didn't actually ask for what optical isomerism was. So they stated that they have, the molecules having identical physical and chemical properties because they look exactly the same. They actually went for this one, but they rotate the plane of polarized light differently in opposite directions. So they actually gave you marks for that only. So define enantiomers. Not really sure why they ignored all the rest, but they gave you mark for this one. And they gave you 1 mark. So you're probably going to get that mark, but the molecules having exactly the same chemical and physical properties. So I guess isko na note this down. They actually went for this answer when they wanted to define enantiomers. As agla part suggests one disadvantage of producing 2 enantiomers in this synthesis. Achha, what's wrong with producing 2 enantiomers? Or what is the synthesis, by the way? Just a second, let's go back. medicine. Okay, now that's important. So tell me why side effects, because the thing is that biological molecules are very shape specific. So one of the enantiomers will work because they're shape specific. Enzyme wo lock and key model, they have a very shape space, like your two hands, right? Two hands are enantiomers of each other. So if you've got a glove of a right hand, only your right hand will fit into it, not your left hand. Although they look exactly the same, but because your glove is very shape specific, it will not. I mean, your left hand will not be able to fit into it. So the same with biological molecules, that they are very shape specific. So one enantiomer will work, the other one will not work, and that will create side effects. So that's why medicine has side effects, because you sometimes produce the other enantiomer, which is the one that's not working. Like you've got a right glove and you should be synthesizing a right hand for it, but you end up synthesizing a left hand. So that left hand will not work with the glove that's right-handed. So suggest one disadvantage of producing so side effects. Usko likha hua kis tarah se? What did he state? I'm probably going to be the same statement, which is that so it's kind of the same way: low yield of biologically active molecule, or reduced activity of the. So it's basically the same thing. Like one of them works, the other one does not work. Because it's kind of the same thing. That's the next one. Suggest a method of adapting the synthesis to produce a single enantiomer. So how do you adapt the synthesis, and how would you produce a single enantiomer? Now this one is important. Chirality. How do you produce a single chiral molecule? Especially in this case. Okay, this is being produced. Which part of the molecule is actually chiral? Which part is chiral, by the way? It's this part, right? That is the part that is chiral. So how would you produce a single enantiomer? That's the only part that's chiral, right? So that is reduction that's happening. And that's simply reduction that's happening. So how would you figure out or how would you produce a single chiral carbon atom molecule? Now let me explain to you what's going to happen. Let me show you some slides. There are two ways of the reaction to proceed. Now over here, over here you've got, I'm just focusing on this thing. You've got a serial bond O and you've got carbon chains, right? Now that's a planar molecule. Planar means that it's completely flat. So if I draw the sideways of this thing, it's going to look something like this. It's serial bond O, and there's this R group that's coming out of the page, so it's fan shaped, and there's one R that's going into the page. So it's like a fan. We're looking at the fan sideways. Now when it gets reduced, hydrogen atoms get added to it. So this carbon is positive because it's a ketone, it's positive. The LLH4 or NaBH4 is going to produce H-1 ions. So these H-1 ions can go and attack the carbon from the top, and they can get added to it, or they can also get the LLH4 H-1 ions, they can attack and attach to the carbon at the bottom. Now, in both cases, you're going to get a carbon that's they're going to be basically optical isomers, because if the H comes from the top and bonds to the carbon, then all the other bonds are going to get pushed downwards. The O and the R, etc., the R1, R2, etc., and all of them are going to get pushed downwards, right? Vice versa, if the H comes from the bottom and attacks it, all the other bonds are going to get pushed upwards. So it's going to be a mirrored version, an upside down mirrored version of this particular molecule. So the problem with ketones is that you're always going to get optical isomers because of the shape. It's a planar shape, and the H can attach from the top. It can attach from either side. That's why this is going to be chiral. Okay, do you understand this? You clear?
Yes, sir.
Acha, so how would you remove one of the molecules in this case? Because you're going to get both of them. You're going to get the other one as well, which is that all the groups are going to get pushed upwards. And the H is attacking from the bottom. Okay, so you understand it's going to be, it will result in both types of enantiomers because of the shape. Okay, this is clear 100%. Is this clear?
Yes, sir.
Or it's when I always remember okay, when you have the mechanism and the starting molecule is planar, that means whatever is getting attached, it could get attached from either side. So you'll get both types of structures. So there's no way you can either, one thing that you can do is you can either change the whole process, because there's no way of stopping either one of them. Like this one is the one that works and this one is the one that does not work. So there's no way you can actually stop the manufacture of the other one. So what you're going to do is there's a thing called you can add enantiomer specific reactions that can help remove one of the catalyst. Okay, so for example, suggest a method for adapting the synthesis. So there are chiral catalysts that are added, which can go and combine with one of them, and that could help you remove them. Okay, so there's a class of compounds, or there are stereochemical reactions which would remove one of them and not the other one. The one that's useful, that stays. The one that's not useful, that is removed. Okay, is this clear?
Yes.
और इसका एकदम वो है 1 second. So let me just explain this one, because there are very few questions on this, okay? So you don't really see them in past papers. So let me just go over this thing once more, okay? There was this, I think even I've lost it, just a second. So I just wanted to show you. It's a key slide, which I'm forgetting where I've kept it, but so I'll show you this in the other one, but I'll explain one more thing over here. Okay, well, I'll explain that. I'll go through that in the next class then, okay? लेकिन ये clear है कि this part clear? This was one type of chiral synthesis. We're going to get both types of products. Is that part clear?
Yes, sir.
Achha, predict the number of peaks that will be seen in the carbon-13 NMR spectrum of this molecule. So carbon-13, that's that focus on the carbons. That's one carbon atom. It's different from the other ones. That's another one. That's different from the other ones. That's second peak. These, I think all the other carbons in benzene are different. None of them are exactly the same. So 6 peaks for benzene. Like this carbon over here is different from this carbon because this carbon is further away from Cl. This carbon is closer to Cl. So the environment of all the carbons is different. Then you have this carbon, which is with OH, that's the 7th peak. Then you have this carbon, which is with 2 H's. That's your 8th peak. Then you have this carbon, which is your 9th. I said these carbons over here, they are exactly the same. They're all CH3s bonded to the same. So there'll be 10 peaks for this molecule. अच्छा, फिर proton NMR spectrum give details. Ising of this molecule is dissolved in D2O, shows peaks in 4 different types of environment. So let's remove this. Now we're talking about carbon. I said now we're talking about carbon 13 NMR, not hydrogen NMR, sorry. So the H's, the benzene H's will resonate together. Not exactly together, it's going to be a multiplet, but at least they would be very similar grouped together. Then what other H do we have? We've got an H over here. So that is different. You've got an OH, that's different. You got two H's over here, CH2. So we've got CH2, we've got NH, and we've got CH3s. The CH3s will all be together. So they're all 3 CH3s. So they're all in the same environment. So, but it's dissolved in D2O. So which of the peaks will not be appearing?
OH and NH.
ठीक है, तो आपकी जो OH है and the NH2 peaks will not be appearing because they're going to get replaced by D+1 ions.
And sir,
हाँ,
आपने बोला है कि बेंजीन के अंदर कार्बन के सारे सेम होते हैं. Why?
नहीं, हाइड्रोजन सेम है, सेम एनवायरनमेंट.
सॉरी, हाँ, कार्बन के डिफरेंट होते हैं. Why?
इस केस में क्योंकि कार्बन डिफरेंट है, लाइक
जो आपने पहले 10 पीक्स बताई थी उनमें आपने कार्बन
हाँ,
को
तो कार्बन
different
over
कहा
here
था.
is bonded to Cl, right?
जी.
Carbon over here is bonded to CH, OH. तो obviously different है.
और बाकी?
फिर बाकी भी this carbon is right next to Cl, so it's obviously different क्योंकि the other carbons are further away from Cl.
Okay.
अगर तो बिल्कुल symmetric होता ना, if it's like this, then they would all be exactly the same. ठीक है, but even if you had one Cl, then this one would be different. ठीक है, these two would be exactly the same. These would be exactly the same, and this would be, there'll be 4 environments, right? So लेकिन यहाँ पे because it's completely non-symmetric, like all the carbon atoms, they're all different.
Okay, understood.
अच्छा, वो क्या है, proton NMR spectrum of this thing is D2O, shows peaks in 4 different types of environments. Environment is a doublet. ठीक है, that's a doublet in the chemical shift range. Give details for each of the 3 other peaks in the proton NMR spectrum of you have to give the chemical shift, the environment of the proton, splitting pattern, and the number of H. So we can just write each one. So the number of H for this one, that's 9 H's, right? Is this going to be a singlet or a doublet or what? Singlet. Neighboring carbon has no H's. NH does not cause splitting to begin with. So it's a singlet. He already gave you for CH, he already told you what it was. I mean, this CH2. He told you that was a doublet. Why? Because the neighboring carbon atom has 1 H. And there were 2 hydrogens that were responsible for this. Then you have this CH. What is this CH going to be? Okay, the neighboring carbon atom, there's no H over here. The neighboring carbon atom over here has 2 H's. So it's going to be a triplet. And there is only one. हाँ जी.
सर वो जो बेंजीन से जो स्ट्रक्चर जिधर से निकल रहा है उधर भी एक कार्बन पे एच नहीं लगेगा?
इधर ये नहीं है.
अच्छा.
वो डबल बॉन्ड है ना. I mean, every carbon atom is making double bonds, right? That ring represents a double bond. Benzene में carbon only makes 3 bonds, or it's attached to 3 atoms because one of them is a double bond, which gets delocalized. Actually, clear, this one is going to be a triplet because the neighboring carbon atom has 2 H's. And then finally you have benzene. Benzene is going to be a multiplet. Benzene is usually a multiplet because halka sa bhi usme difference hona, so it's going to be multiplet. So that's what it's going to be, splitting pattern. You can write about the environment of the protons, and you can, by looking at the data booklet, you have a data booklet actually attached to it. So benzene H's, where's benzene H's? This one, that's 6 to 9. So you can talk about this. This is 6 to 9. This one is your normal alkyl. So that's what is your normal alkyl? That's 0.92. 1.7. Okay, you've got the other one, the CH2 that's right next to NH. That one is also would be given over here. I don't know if it's given or not. A CH2 that's right next to N, or an electronegative atom, I guess that would work. Probably 3.22, 4. The CH2N, he gave that already because that's not in the data booklet. So he already told you what the chemical shift value for that is. You've got a CH which is next to NOH, so we can talk about that. So we've got a CH that's next to NOH. Probably this one, 3.22, 4. So this one over here, CH that's next to NOH, that's 3.22, 4. Is clear?
Yes, sir.
So the thing with benzene is because there's some slight variation, it's usually always a multiplet. It's hard to actually guess what the spreading pattern is for benzene. I'll just check the marking scheme. It's probably going to be a multiplet. Remember benzene, the neighboring carbon has no H's, right? I mean, the neighboring carbon atom over here has no H's. Even this one has no H's. So the spreading is not happening because of that. It's happening because all the H's are not exactly in the same environment. They're not exactly the same. So let's check this one out. Okay.
Sir,
हाँ जी.
लास्ट टाइम डेटा बुकलेट में वो बताते थे कि 2,4 विड्रॉइंग ग्रुप और डोनेटिंग ग्रुप में आपके कौन से मॉलिक्यूल्स आते हैं.
हाँ, उस पर बता.
तो अब बताएंगे क्योंकि अब तो हमारे पास डेटा बुकलेट नहीं है, तो क्वेश्चन में दे दिया करेंगे. ओह,
सर यहाँ पे नहीं बताया वाला.
राइट.
वो क्वेश्चन क्या था ना, वो 246 वाला था. They didn't tell you what it was. As I said, this one, let's just quickly go through the answer for this one. So 6 to 9 benzene is a multiplet. Okay, they always go for multiplet. 0.9, that was 9/8 singlet. Okay, we did that. CH3 was the environment, and the last one was the 1H. That was the triplet. Okay, that is next to O. Okay, we went to alkyl next to an electronegative atom. So that's 3.2 to 4. So we answered all of that. Okay. So ठीक है, इस पे और कोई क्वेश्चन रहेगा इसमें in the same question? Just 1 second. नहीं, we're done with this question. चलो ठीक है, वो मैं I'll send you the I'll try and send you the वो chiral part, like chiral synthesis. ठीक है, it's a very small thing, but very rarely it's going to be asked. But keep that in mind. ठीक है, I'll try and find the animation for that. चले, okay.
Okay, sir.
Yes.